All right, good day, everyone. Welcome back to class. Today, we want to take a review class on the topic chemical equilibrium. Chemical equilibrium. Now, we all know that most chemical reactions are just combination of some species, let's say A and B, to give a product, let's say C and D. Now, this is just a chemical reaction, and there are some reactions of this nature in the sense that if A is combining with B to form C and D, then C and D will combine together again to form back A and B. So this is where this chemical equilibrium is coming from in this kind of reaction. Now, this type of reaction is what we call a reversible reaction. A what? A reversible reaction. Now, in a closed system, most reaction stems or likes to be or reversible. Some reactions likes or tends to be what? Reversible. So this A and B now, we might decide to write it again like this: A plus B, then form C and D plus D. Then C and D combines again to form back A and B. Now we may say, okay, let's say if the equation is not balanced, we just put M here to balance A, put N to balance B, put P to balance C, put Q to balance D. So this N, P, Q are just stoichiometric coefficients, or the how many moles of A, B, C, D we have there. But the reactants are the A and B, so we call them the reactant. Is the reactant. Then the products are the C and D. Call these ones the what? The product. Now, chemical equilibrium is a state. Chemical equilibrium is not a state in which this reactant and this product are present in a concentration that has no further tendency to change. They might not necessarily be having the same concentration. No, I'm not telling you that they have the same concentration. No, I'm telling you that the concentration of this reactant and the concentration of this product will be something like let's say will be stable, in which there will not be changes again. That period in which there's no change in their concentration, we call that period where we have our chemical equilibrium. So it's just a state in which the reactant and the products are present in concentration that have no further tendency to what? To change. Now we have a reaction that can either be heterogeneous or homogeneous. Now, for example, if you check the nature of reacting species, let's say we have something like this. If we have something of this nature, let's say we have A plus B to give C plus D. If we combine A and B to give C and D, and let's say the nature of A is gaseous, B is also gaseous, C is also gaseous, and D is also gaseous. This is called a homogeneous reaction. Why is it a homogeneous reaction? Because all the reactive species check. A is in gaseous state, B is in gaseous state, C is in gaseous state, and D is also in gaseous state. It's not when all of them are in gaseous. No. When everything are in the same phase, it's either all of them will be in gaseous state or all of them will be in solid state. Let's say A will be solid, B will be solid, C will be solid, D will be solid. It's also homogeneous. If all of them are in liquid state, it's also homogeneous. So when the reaction is present in what's it called, in the same phase, all the reacting species, they are the same phase of matter. Remember, we have solid, liquid, and the gaseous state of matter. So when everything are in the same phase, let's say the same phase, like solid, everything is solid, or everything is liquid, or everything is in the gaseous state, we call it a homogeneous reaction. Then what about heterogeneous reaction? Now let's assume we have something like this. Let's assume this A is in the gaseous state, B is in solid state, C gaseous, D, let's also say gaseous. So if you check now, A is in gaseous state, B is in solid state, C is also in gaseous state, then the D is also in gaseous state. If you check, we have gaseous, but solid. Everything are not present in the same phase. B is not in gaseous state, it's not aligning with others. So something like this, in which one or more of the reactive species are in different phase than others, we call such a reaction heterogeneous reaction. So equilibrium we are going to get here now is heterogeneous equilibrium. Then the equilibrium we do have in the homogeneous reactions is a homogeneous equilibrium. Now let's look at factors that will affect chemical equilibrium. Now we have different factors that can alter the equilibrium position of a chemical reaction. We have different factors. Example of such a factor, we have the following. We have temperature. Temperature can affect chemical equilibrium. We have pressure. Then we have concentration. Then catalyst will only speed up the reaction to not affect the state of the chemical equilibrium. We will not affect the position of the chemical equilibrium, but we just speed up the reaction. Catalyst affect rates of chemical reaction, so it will not affect the chemical or equilibrium position. So these three factors for now are what we'll be discussing: temperature, pressure, and concentration. And how do they affect this chemical equilibrium? Remember, chemical equilibrium is when the reactants and the products are present in concentration that has no further tendency to change, and this equilibrium position can be affected by temperature, pressure, and what? Concentration. Okay, what is the meaning of reversible reaction? A reaction that has this stroke 1, 2. What is the meaning of that? We say we have a reaction A plus B to get C plus D. Now, this is something like a reversible reaction. And a reversible reaction is a type of reaction that can proceed to both forward and backward direction. That's what we call reversible reaction. So this is the forward reaction. While this is the backward reaction. So take note of that. So this side is called the product, or the right hand side, while this other side is called the reactant, or the left hand side. So here's this side is the left, while this other side is the what? Is the right hand side. So now let's look at how to write equilibrium constant Kc for a given chemical reaction at equilibrium. We use the law of mass action. The law of what? Mass action. That is the law we use if we want to write the equilibrium constant of a given chemical reaction at equilibrium. Now let's look at it so that we can just move on. Now this law states that for a given chemical reaction at equilibrium, let's say A plus B to give C plus D. And let's say we want to balance them. We have M, we have N, we have P, we have Q. Now, for a given chemical reaction at equilibrium of this nature, now you're seeing the arithmetic product of the terms in product, remember, this side is the product, while this side is the what? Reactant. Remember that. So now telling us the arithmetic product. Arithmetic product means multiplication. When you multiply something, that is meaning of arithmetic product of the terms in the product. Which terms are in the product? The C and the what? And the D. That are the terms in product. P and Q are just numbers of moles of C and D. The arithmetic product of the product divided by that of the reactant, each raised to their numbers of moles or each raised to their stoichiometric coefficients in the balanced equation is constant. Each raised to their what? Stoichiometric coefficient in the balanced equation is constant. So that constant helps us to write out this reaction now in terms of equilibrium constant. So we can just say Kc, equilibrium constant, is equals to, we said the arithmetic product of the product. The product is C and D. That is the product. That's the product we're having. While the reactant are A and what? And B. We may have one product too, just one thing the product, one thing the reactant, but not be two. Check out. This one is just illustration. Then each raised to their stoichiometric coefficient or each raised to their numbers of moles. So you raise C. How many moles we have? P mole of C equal P here. We have Q mole of D equal Q here. We have M moles of A equal M here. Okay, here equal M here. Sorry about that. M. They have N moles of B. You put N here. So this is how we do write our equilibrium constant. Just multiply what you have in the product, raise them to the number of their moles, divided by what you have in reactants, raise them to the numbers of their moles. So the only thing you should take note of here now is if any of these reactive species are pure liquid or solid, you will ignore them after everything. We just ignore. For pure liquid or solid, we don't include them while writing equilibrium constant. So let's look at some few examples. Now, let's see if we are at sulfur dioxide and oxygen gas to form sulfur trioxide. So to balance this equation now, we have 4 oxygen, check. We have oxygen to be equal to 4 in the left hand side, check. We have 4 here, 2 plus 2, we have 3. So it's not balanced. So you have to balance it. To balance this now, what we are going to do, okay, let's assume we add 2 to this place. We have 2 sulfur. We also have 2 sulfur. Let's check. We have 4 plus 6. 2 times 3 is 6. So we have balance equation now. 2 times 2, that is 4, plus 2, that is 6. 2 times 3, that is 6. Oxygens, okay. We have 2 sulfur. We also have 2 sulfur. So this equation is 100% balanced now. So now we can now write our chemical equilibrium. The next thing is to check the nature of the reactive species. Now this is in the gaseous state. This is the gaseous state. This one is the gaseous state. So to write the equilibrium constant now, we just write Kc is equals to product. Look at the product here. This is the product we having, just one term. So you write out the product. Don't write out the this thing yet, coefficient. Leave the coefficient alone. Write the terms only. Just write the reacting species in the product, which is just SO3. Then the raised to power. How many moles of SO3 do you have? We have 2 moles. So the 2 will now be here. Divided by, what do we have in the product? We have SO2. We have SO2. Raised to power, how many moles? We have 2. Raised to power 2. Then times, we have oxygen here. O2. How many moles? Just 1. So there's no need of saying raised to power 1 because it will not amount to anything. So you just forget about that. So this is what you're going to have. Then you now check. Do you have any solid or liquid? No. We have this. Everything is in gaseous state. So this is the equilibrium constant for this given chemical reaction. Now let's look at another one. Check. Ensure you understand this. It's very, very important. Let's assume we want to combine carbon solid and oxygen gas to form carbon monoxide. As we want to do this, so to balance this equation now, we have 2 oxygen. Just put 2 here, then you put 2 here. The equation will be balanced. So to write the equilibrium constant now, you just write Kc equal to the product. Look at the product here. We have Cu as our product. Then raised to power the number of mole divided by the reactant. We have C raised to power the number of moles. Then we have O2 raised to power the number of what? Of mole. There's no mole in the pool. We just have 1 mole. So there's anything to raise to power there. You now check either of these terms now. Is there anyone in solid state or liquid state? Look at this. It's in the solid state. So it's carbon. So you strike it out of the equilibrium constant because it's not supposed to be there. So what we left out now will be, because we are removing this because it's in solid state. That's why we are removing it, because we don't add solid or liquid to this equilibrium constant. So we're going to have CO raised to power 2 over O2. This is what we are going to have at the end of the day. So this will be our equilibrium constant. CO raised to power 2 over what? Over O2. Now let's look at others. Now for the reaction, let's say we have 2H2 in gaseous state plus O2 in gaseous state to form 2H2O. Also in gaseous state. So what is the equilibrium constant? So that you write K subscript C, or you just capital letter K. So that will give us for the product we have H2O. Then that's H2O. Then raised to power 2, which is the numbers of mole, divided by the reactant, which is H2 raised to power 2. Then O2, there is no power. Then you now check, is there any solid or liquid? No, everything is in gaseous state. So this will be the answer to this. So for homogeneous equilibrium in liquid state, in gaseous state, nothing will always leave. So I hope you know how to write equilibrium constant now. So let's look at Chatelier'S principle. How does temperature, pressure, and concentration affect chemical equilibrium? Now let's look at Chatelier'S principle. Now Chatelier'S principle is telling us that if we have a chemical reaction at equilibrium, for any reaction at equilibrium, if any of these reacting something like what do you call it, any of these factors is altered, let's say if we alter the temperature, or we alter the concentration, or we alter the pressure, we alter any of them, the equilibrium position will shift as to oppose that alteration you are making, or that changes you are trying to make. So equilibrium position will shift as to oppose that change. If you change the temperature, the equilibrium will shift. Change the pressure, change the concentration, the equilibrium position will shift. It's either going to shift to the reactant, which is the left, or it will shift to the product, which is the right hand side. So let's see where will it be shifted to, where we are changing the temperature, pressure, and so on. So let's go. Now, firstly, let's look at for temperature change. If we change the temperature, how will the equilibrium position react? Now, there are some things you have to check in this change in temperature we are going to be looking at, which is this delta H they call enthalpy change for a given chemical reaction. Now, if this enthalpy change is positive, it means the reaction is endothermic. It's going to take heat from the surrounding. Then if the delta H, which is the enthalpy change, is negative, it means the reaction is exothermic. For negative enthalpy, reaction is exothermic. For positive enthalpy, reaction is endothermic. So that will be the stuff that will be guiding us when we're looking at temperature change. So if we look at some reactions, we have some reactions that are exothermic. We have others that are endothermic. Now let me look at first reaction, which is N. If we add, let's say we react this nitrogen gas and oxygen gas to form nitrogen monoxide, which is 2, and it's still in the gaseous state. And for this reaction, delta H is positive. Let's say delta H is positive. So that shows that the reaction is what? It is endothermic. It is what? Endothermic. Why? Because delta H is what? Positive. Now, the next thing is to check. If the first thing you check for change the temperature, the first thing you check is to check whether the reaction is either exothermic or endothermic. For this one now, this particular reaction is endothermic. So you mark it out, endothermic. The next, you take note of this statement, or take note of this methodology, or take note of this rule. If a particular reaction is endothermic, for an endothermic reaction, if you increase the temperature, equilibrium position will shift to the right, or we favor the forward reaction, or we favor the product. For an endothermic reaction, if the temperature is increased, equilibrium position will shift to the right hand side. You take note of that. So that means for an endothermic reaction, if you decrease the temperature, reverse will be the case. If increase, we cause it to shift to the right. Decrease, we cause it to shift to the left. So take note of that. It's very, very important. Then for exothermic, it will be the opposite of endothermic. Now we said for endothermic reaction, increase the temperature, equilibrium position shift to the right. Decrease, move it to the left. Now for exothermic now, if you increase for exothermic, which is opposite to this endothermic, exothermic is negative for DH, delta H. So for that exothermic now, if you increase the temperature for this negative one, the equilibrium is either we now move to the what? To the left, because for endothermic, if you increase, move to the right. For exothermic, if you increase, is going to move to the left. You just be opposite of that endothermic. So if you understand the endothermic, you are already good to go. There's no need of cramming. You don't cram anything here. You just understand the statement. For an endothermic reaction, if you increase temperature, equilibrium position shift to the right hand side. So automatically, if you decrease the temperature, it's going to shift to the left, because you cannot increase and it will shift to the right. If you decrease, you shift to the right. No. We said if you increase, it will shift to the right. So automatically, if you decrease it, it's going to shift to the left. Then for exothermic now, will be the opposite of endothermic. Since we are shifting to the right by increase and shifting to the left by decrease in endothermic, for exothermic now, it will just be opposite. If we are shifting to the left for exothermic now, to be when we are something like since we already said if we increase temperature for endothermic, it's going to shift to the right, decrease, shift to the left. For exothermic, increase to the left, decrease to the right. So it will not be reverse of each other. So if the reaction is exothermic now, if you increase temperature, it will move to the left. It will not be the right again. So you write that one down. For endothermic reaction, and increase the temperature will cause equilibrium position to shift to the right. That's for endothermic. For endothermic reaction, and increase temperature will cause the equilibrium position to shift to the right. While for exothermic reaction, and increase temperature will cause the equilibrium position to shift to the left. So take note of that. It's very, very important. So for this question now, since this question is endothermic, if you increase temperature, equilibrium position will shift to the right. If you decrease temperature, it will shift to the what? To the left. So take note of that. It's very, very important. So let me look at another question under this temperature. Now for this particular reaction now, you can check delta H is positive. So that means the reaction is still what? Endothermic. So if you increase temperature now, if you increase temperature, let's say we increase temperature, equilibrium position will shift to where? If we decrease temperature, equilibrium position will shift to where? So let's check. For increased temperature, we said it will shift to where? The right. To the right. So automatically, if you decrease the temperature now, it will shift to the what? To the left. So right means product, left means reactant. Right also means forward reaction, left also means the backward reaction. So also take note of that. It's very, very important. So for an endothermic reaction, if you increase temperature, equilibrium position shift to the what? To the right. If you decrease the temperature, it will shift to the what? To the left. So take note of this. So let's look at just one more for this. We'll move on. Now for this particular reaction, delta H is negative. It means the reaction is what? Exothermic. Is what? Is exothermic. So if you increase the temperature, what is going to happen? And if you decrease the temperature, what is going to happen? So let's check. Remember, for endothermic, we said if we increase temperature, we move to the right, decrease, move to the left. So for this one, reverse will be the case. For this one, if you increase the temperature again, in which the reaction is already something like hot, what will happen is that the thing will shift to the left. Equilibrium position will move to the left. If you decrease temperature, then the forward reaction will be favored. Equilibrium position will shift to the right when you decrease the temperature. Just a reverse of that endothermic reaction. So please take note. It's very, very important. For exothermic now, increase temperature cause it to shift to the left. Decrease temperature cause it to shift to the what? Right. So take note of this. It's very, very important. Now let's look at effect of pressure. Effect of pressure. Effect of pressure. Effect of pressure now. Now, how does pressure affect chemical equilibrium? Now, to get the effect of pressure in the chemical equilibrium, what you need to get is to check how many moles of the reactive species are there, and also ensure you take regards to only gaseous reactants or products. So we do consider gases only in this place when we are talking about effect of pressure in equilibrium. You take note of gases only. Now let's say we have something like this. We have something like this: N2 gaseous plus 3H 2 gaseous, 3H2 gaseous to give 2N to give 2NH3 also gaseous. This one we don't check for endothermic or exothermic. No, just check how many numbers of moles do we have in this left hand side and how many numbers of moles do we have in this right hand side. And let's check. We have 1 mole of nitrogen here. Then we have 3 moles of hydrogen gas. So 1 plus 3, what's that one? 1 plus 3, that's equals to 4 moles. So we have 4 moles of reactant. Then the product, so let me just say the reactant now is equals to 1 mole plus this 1 mole plus 3 moles that is equal to 4. Then the product is equals to just 2 moles. There's another thing there again. Don't start using to multiply. No, just take only the coefficients. You have 2 moles here. So we have 2, we have 4. So if you increase pressure, let me just write N. If you increase pressure or you decrease pressure, what will happen to this particular reaction? Now take note of this as well. Take note of this statement. Write it down. Now, an increase in pressure will cause equilibrium position to shift to the side with lesser numbers of moles. An increase in pressure will cause equilibrium position to shift to the side with lesser numbers of what? Moles. So please take note that it's very, very important. So if you increase pressure, equilibrium position will move to the side that have lesser number of moles. If you decrease pressure, equilibrium position will shift to the side that have higher numbers of moles. So please, you take note of that. It is very, very, very important. It's very, very what? Important. So let's check now to see what we are going to get. Now let's check to see if we increase this one. If we increase pressure here now, what are we going to have? We have 4, we have 3. Equilibrium position shift to the what? To the right. We go to shift to the right. Since the right has lesser number of moles, then if we decrease the pressure, since the volume of this place is bigger now, it will move to the left for decrease. But for increase, it move to the side that have lesser number of moles or lesser volume. Let me look at another one so that you get it better. All right, now let's look at this question. Let's say we have N2 O4 gaseous to form 2N O2 gaseous. Let's say we have this. I want to check the effect of pressure when we decrease the pressure or increase the pressure. How many moles do we have here? We just have 1 mole. So we have 1 mole for reactant. We have just 1. Then for products, we have 2. For product now, we now have it to check. Product is higher than reactant. Remember, increase in pressure we favor the side that have lesser number. For the side that have lesser number. So for you to have good product here now, what do you need to do? You need to decrease the pressure. Why? Because if you increase it, it will move to this side that have the lesser number. So to get good product here now, you decrease pressure. So a decrease in pressure here, we favor the right hand side, which is the product. While increase in pressure, we favor the left hand side, which is the reactant. So for you to get good products in this question, they can ask you to get a good product or to get your product to be favored. What do you need to do to this reaction? What do you need to do to the pressure? Are you going to increase the pressure or you decrease the pressure? Since the what is it called, the forward reaction is already having higher higher number of moles, you don't need to increase pressure again, because if you increase pressure, it will move to the side that have lesser number. So what you don't need to do, you just decrease it, because if you decrease the pressure, we go to the side that have higher number, but if you increase it, you go to the side that have lesser number. So decrease, move to the side that have higher, increase, move to the side that have lower. So take note of that. So for this one now, since the product is already having higher number of moles, you have to decrease pressure to have more product, or to have your equilibrium position shift to the right, you have to decrease pressure. But if you have that both of them have the same number of moles, let's say this one is 1, this one is also 1, or this one is 2, this one is also 2, pressure may have no effect on that kind of reaction. So let's look at the last one, which is effect of concentration. Now let's look at effect of concentration. Effect of concentration in chemical equilibrium. Now please take note of this. Take note of this. For concentration, we favor the side that have lesser concentration. Just like if you increase concentration, the equilibrium will move to the side that have lesser what? Concentration. Therefore, pressure just now, if you increase pressure, we move to the side that have lesser number of moles. If you decrease pressure, you move to the side that have the higher number of moles. Now, for example, let's say we have a particular reaction. Let's say we have a particular reaction in which we are reacting hydrogen gas with iodine gas. Let's say we have H2 gaseous plus iodine gaseous to form hydrogen iodide gaseous. Hydrogen iodide gaseous. So we just put 2 here. Now, for concentration now, look at 2 things we are going to go. If you increase the reactant, the concentration of the reactant, increase means by adding more of the reactant. For example, you can add more iodine, or you add more hydrogen gas. The equilibrium position will shift to the right. If you increase the reactant, the equilibrium position will shift to the right. For example, now the concentration here and here, they have been concentrations that have no further tendency to change. So if you decide to change this one now, then this one will also react in order to annul something like the equilibrium position will have to shift in order to annul that change. So what will happen is that if you increase the concentration of one side, the other side will be favored. I don't know if you understand what I'm trying to say. If you increase the concentration of this side now, this other side will be favored. Then if you increase the concentration of this side, then this other side will be favored. That's just it. If you add more, for example now, look at the things you have to get here. If you add more something like a reactant, if you add more reactant, the product will be favored. If you add more product, the reactant will also be what? Will be favored. That's just how it is. So if you add hydrogen iodide, equilibrium position will shift to the reactant, which is the left. Then if you remove, that's another way to something like something like illustrate this. For example, now if I remove more of this iodine, that means I will have less concentration in this place. I will have reduced the concentration of this place. So if you reduce the concentration of one side, equilibrium position will move to that side. If you increase the concentration of one side, equilibrium position will move to the opposite side. Take note of that. So if I remove this hydrogen gas now, equilibrium position will shift to the what? To the left. Because I'm reducing the concentration of the reactant. So equilibrium position will shift to the side that have lesser concentration. Then if I decide to remove this hydrogen iodide, maybe say I'm removing this one as it's being formed, I'll be removing them. Then I'll be having more of the equilibrium position move to the right hand side. Right hand side will be favored if I am removing this hydrogen iodide. So 3 questions can be asked in this place. For example, they can ask you if the concentration is if more reactant is added, If more reactant is added, where will the equilibrium position move to? If more reactant is added, remember, if you add more reactant will have more concentration, and equilibrium position will move to the what? To the right hand side with lesser concentration. Then number 2, they can ask you, if more hydrogen gas is added to the system, what will happen to the equilibrium position? If you add more hydrogen gas, that is still a reactant. Equilibrium position will shift to the what? To the right hand side. Number 3, they can ask you, if more iodine is added to the system, what will happen to the equilibrium position? It will shift to the what? Right, because it's still a reactant. Then if more hydrogen iodide is added to the system, what will happen? The equilibrium position will shift to the what? To the left now in this case. So if you add product, it will shift to the left. If you add reactant, it will shift to the right. If you remove product, it will shift to the product. So for adding, okay, let me just say this, then I'm done with this. So please just try and get it once and for all. Now let me just say this last thing. If you add for add, let's discuss adding. If you add product, equilibrium position will shift to the reactant. If you add reactant, equilibrium position will shift to the product. Just take note of that first. So that means if I add hydrogen iodide, equilibrium position will shift to the left. If I add either of the hydrogen gas or iodine, then if I added any of them, because they are the reactant, equilibrium position will shift to the right hand side, which is the product. That is for add. Now let's look at remove. If I remove hydrogen gas, equilibrium position will move to that side you are removing something from. If you add, you move to the opposite side. But if you remove, if you move to that side you are removing something from. So if I remove hydrogen gas now, equilibrium position will move to this side, favoring the left hand side. If I remove iodine, it will move to this side, favoring that side you are removing something from. Then if I remove hydrogen iodide, equilibrium position will shift to the right hand side. This is how best this can be explained. So if you have any question, please make sure you put it in our comment section so that we will work on it. So lastly, let me just use one question to just illustrate everything, then we are good to go. Now let's look at this particular reaction. Delta H is negative, which shows us that the reaction is what? Is exothermic. Is what? Exothermic. Now for this exothermic reaction, now for temperature change first, if I increase the temperature, where will the equilibrium position shift to? It will shift to the left because it's exothermic. Then if you decrease temperature, equilibrium position will shift to the what? To the right. So please take note of that. Then number 2, for pressure, this has 1, that is 3 moles. So I have just 2 moles. So if I increase pressure, it will move to the side I have a lesser number of moles. If I decrease pressure, it will move to the side I have the higher numbers of moles. Then that is just that. Then lastly, for concentration, if I remove either hydrogen gas or oxygen gas, the equilibrium position will move to the side I'm removing something from. That's from concentration. Then if I add more hydrogen gas or oxygen gas, equilibrium position will shift to that side that have lesser concentration. So if I add the product and the reactant, it will move to the product. If I add product, it will move to the reactant. If I remove product, it will move to the product. That is all. So thank you. God bless you all. Don't forget to subscribe, like this video, share it to others. Drop your comment in our comment section so that we will take care of and handle everything. Thank you.